So today we're going to look at the solving of some more advanced trig equations. And by that I basically mean trig equations in which the angle is not just an x or a theta, but it's something multiplied by theta and added and stuff, and there's more things going on with the angle. So in solving these, we want to connect our algebraic and graphical understandings and processes, because sometimes one way is more appropriate than another, or more necessary. So I'm going to begin this question, solve sine 2 theta equals a half exactly over this interval. I'm going to start by thinking about it graphically. And to do that, I'm going to think first of all of just a regular sine 2 theta graph, which is a sine graph with an amplitude of 1, a value, and the period. It's been compressed horizontally by a factor of a half, so that would be regular period 2 pi divided by 2 and new period of pi for this particular graph. And if I were just to graph that, a little bit of it, my ratios would oscillate between -1 and 1, and my period would be pi. There's one cycle. Now we're asked to solve on this equation between 0 and 2 pi, so I'm going to extend my graph for another cycle. Remember, another way to think about the 2 in this position is that I have 2 cycles of sine in the span of where usually I only have 1. And then we want to connect that to this equaling a half. So my second equation, y2 is a half, and y equals a half is a line, horizontal line like so. And we know that when we solve graphically, the first coordinates of the points of intersection give us the solution to our equation. So we can see visually here that there are 4 solutions, which is one of the advantages of looking at the solution graphically. I can see that I should get 4 answers. And I could go into my calculator, get the points of intersection, take the first coordinate, and I'd have my answer. The problem is I would not have my answer exactly. And so this is now forcing me to do this question algebraically. Alright, so starting with my question, sine 2 theta equals a half. What I like to do in situations where the angle is a bit more complex than normal is I'm just going to assign that to a variable. Let b equal 2 theta and do a substitution. And now this looks like an equation that I've solved before. I'm going to go through my steps. Sine has a positive ratio in quadrants 1 and 2. So I know that angle B, which is what I'm talking about right now, is in quadrant 1 or quadrant 2. And I know that both of these angles share the same reference angle. We've talked about all this before. And we know that the reference angle of B can be found by calculator, but because we're doing this exactly, we can't use the calculator because the calculator in general doesn't give exact values. But we'll recognize this ratio as one from one of our special triangles. And so if I think sine as the vertical y over the radius in both quadrants, 1 over 2, I know by Pythagoras that this is root 3, and more so I know that this is a special triangle, and I know that the reference angle, the angle across from the 1 in this special triangle, is 30 degrees, which is pi over 6 radians. And I'm doing this in radians because my interval is given in radians here. That's how I know. And so angle B in quadrant 1 is pi over 6, and in quadrant 2 it would be pi minus pi over 6, better known as 5 pi over 6. Now that's angle B. Let's now revert back to what the angle is that we're asked to solve for, which is 2 theta. So angle 2 theta would be pi over 6, or 5 pi over 6. And so to get theta, divide both sides by 2, so I get pi over 12, and I get 5 pi over 12. And so I have 2 solutions. But remember that when we thought about this visually, we saw that we were supposed to be getting 4 solutions. So if we connect this back to our graph, our theta pi over 12, that's really this angle right here that we've calculated. And this angle, 5 pi over 12, is there. And you say, well, where are our other 2 solutions? Well, our other 2 solutions are 1 cycle away from the given solutions. So I know pi over 12, but I know that there's an answer one period or one cycle away as well. And because the period of the graph was pi, I can get this answer by adding on pi. And I can get this answer by adding on pi. 13 pi over 12 would be the third angle. 17 pi over 12 would give me my 4 solutions. Now, of course, these solutions are the solutions over just the interval 0 to pi. If I'm asked for the solution over the set of real numbers, the idea is the same. This meaning, of course, that I want to extend my graph endlessly and get all angles where the sine ratio is a half. I simply take my core answers, pi over 12 and 5 pi over 12, and I add a period, or 2 periods, or 3 periods, or subtract a period to go backwards. So I say that by saying n pi. Where n is an integer. In our next example, we're going to look at a situation that is more complex and that we cannot solve using exact values. In other words, we will definitely need to use our calculator. The first thing we need to do is we need to isolate the cosine part. So I can subtract 10 on both sides. Divide by 6, which would be negative 1/3. And I'm going to move to my calculator in a moment. Just before I do that, just a reminder that this number is the number that affects the period. So the period of the graph, of the cosine graph here on the right, y equals that, would be 2 pi divided by b, which is 2 pi multiplied by 4 over pi, which comes nicely out to 8. Now, just before I go to my calculator, let's just do a little hand sketch just so we have an idea of what's happening. We have a period of 8. We have a cosine graph. And we know that this would be 4. This would be 2. This would be 6. And the other thing that's going on with this graph is that the cosine graph is being shifted 2 units to the right. And the graph's going to come back down like that. Okay, so let's just see the calculator. So I have the cosine. Now just watch all your brackets here. Pi over 4. X minus 2. Let's just be sure all of that piece is within the angle. And the other graph, negative 1/3. Our window dimensions, since the period is 8, and I want to see mostly one cycle, I could go from 0 to 8. But I do have a shifting factor happening, which is 2 to the right. So maybe I'll just make this back here negative 2 and 12, just a little bit bigger and smaller than 0 to 8, which covers the period. And then down below here, the amplitude of the graph, it's a 1 cosine graph, so negative 2 to 2. And let's bring up the picture. My graph is matching pretty much what I have in blue up above here. And now we're cutting it at y equals negative 1/3, and we want the points here and here, because the x coordinates here give us the solution on our first cycle. And despite my shifting, that is still the first cycle to the right of the y-axis. So I need to find these 2 points, the x coordinates. So back to my graph. Second function, trace, intersect, first function, second function. Here comes it 4.43 rounded off. I'm just going to store that value. So that's really the x coordinate right here. And the other one, second function, trace, intersect, first curve, second curve. Let's go close to the second one so it finds that one. 7.57 rounded off. And those are the solutions on the first cycle, but since I want all solutions, I'm going to have to add on my period, which is 8, multiple times, n times. And so there's my general solution. So I've solved this equation graphically using the intersection of two graphs. I could have set the equation equal to 0 and used one graph by finding the x-intercepts. Now let's look at how to do this problem analytically. So I brought back my original equation, and I'm going to think of this entire piece as my big angle, B. Okay, and so angle B has a negative cosine ratio when the angle is in quadrants 2 or 3. And what both of these angles have in common is a common reference angle. So I am going to find the reference angle for angle B by doing the inverse cosine of the positive ratio. I can't do this exactly because I don't know what angle has a ratio of 1/3. It's not a part of one of my special triangles. So off to the calculator I go. Inverse cosine of 1/3. And that's giving me an angle of 1.23. Now I'm going to store this number in memory location C. Remember, no rounding off to the end, just write down some numbers so we know you're on the right track. So therefore angle B is, from my diagram in quadrant 2, we know that it's pi minus the reference angle. And in quadrant 3 we know that it's pi plus the reference angle. Alright, now it's time to bring back the fact that B is this big expression. So what we're saying is pi over 4 times x minus 2 is equal to this, or pi over 4 times x minus 2 is equal to this. And now we have two separate equations to solve. Alright, on both equations I could multiply both sides by 4 and divide by pi, and so that would give me and then we have to add 2 to both sides. Okay, and if we decimalize these two, we should get the same answer that we got back here, these two numbers. So 4 divided by pi times pi minus my reference angle, which is stored in C, plus 2. Here's my 4.43. I'm at the end, so I can round off. And since we're doing a general solution, we can add on our period 8 n times. And then typing in the other expression, and my calculation is the same except that it's a plus, as you'll see here, plus the reference angle plus 2. So let's just copy the entry, second function entry, brings that back. Let's just backspace over the minus to a plus, and 7.57. And so I've solved this equation both graphically and analytically.